92. Okay. Guys, even if you're on Zoom, when we ask questions, we would appreciate it if you actually responded because you know you're part of the class. I know I can't see you. It's unfortunate that I can't fit you all in class, but you must be part of class. And so you don't want to be alienated and left out just because you're on the wrong side of the E channel, right? So, morning
Hey,
again.
can I see your microphone for a minute? There's some kind of interference going on. You can keep going.
Okay.
The ceiling mics will pick up until I get this fixed.
All right. So, guys, can you hear me?
Just give me a second.
So, uh, so here's where we were. We've seen that training neural networks was a problem of empirical risk minimization.
Check 1, 2.
So why did we call it empirical risk minimization?
Check.
Guys, shut your laptops, please. So, and so the way we define it, how did we define the empirical risk of the law? That was
All right, try this.
empirical risk,
It's
right?
still kind of quick. I'll see. You might not.
So that wasn't just the empirical risk, right? How did we define the empirical risk, guys? Anyone remember? Shut your laptop, man. Yes. I know. Okay, go ahead. So how did we define the empirical risk?
The average loss over all the.
So we defined, correct. So we had we defined a divergence function. What was the property of the divergence function? It was differentiable, and it had a divergence function had a property that it was zero only when the two arguments were the same. When the two arguments were not the same, it was always positive, right? And so we defined a divergence on each training instance between the actual output of the network Y and the desired output. We averaged it over all of the training data, and the assumption was this average somehow captured the actual integrated expected divergence between the network output and the training data and the desired output, right? And this is what we minimize. So let's see how we can do it today. We're going to be using gradient descent, which we saw in the last class. Now, before I continue, I'm going to introduce some notation just to clarify things. We are going to assume a layered network. And so each layer has a number of neurons. The subsequent layer also has a number of neurons. So I'm going to denote my variables like so. Wij superscript 2 will be the connection from the ith neuron in the first layer to the jth neuron in the second layer. The superscript represents the target layer. The second index represents the target neuron. The first index represents the source neuron, right? So also Bj superscript 2, that means that it's the bias for the jth neuron in the second layer. Is that making sense at all? Right? Because we're going to keep using this notation. And so this was the gradient descent approach. Our parameters were the complete set of weights and biases. And we initialized the parameters, and then we defined the gradient descent was performed by always walking against the gradient, right, at each step. So you always took a step from the current estimate going backwards by some step size against the gradient. And so here was our total training loss. It was the average error across all training instances. This is what we are trying to minimize. And this is so, if I actually expand my gradient descent out, how did we define the gradient? What was the gradient? Pardon me? The direction of steepest descent. But what were the components of the gradient? The partial derivatives with respect to each of the variables, correct? So now, when I write out a gradient descent in terms of for the individual components, this is what you're going to get. Each parameter is going to be moved against the partial derivative of the overall loss with respect to that parameter, right? Everyone with me? So for every, now this makes sense. What does d loss over dw tell you? D loss over dw tells me whether changing the parameter, how changing the parameter is going to modify the loss. If d loss over dw is positive, it means that anytime I increase the parameter, what will happen to the loss? Decrease, right? And so, and if, which means, wait, if d loss over dw is positive, what happens to the loss when I increase the parameter w? It goes up, right? So what must I do with the parameter? Decrease. So basically, for every parameter you're checking, whether increasing the parameter will increase the loss or decrease it. If it's going to increase the loss, you decrease the parameter and vice versa. That's it, right? So simple. And so this term, d loss over dw, is what we need to be able to estimate. And so writing it out, there's your loss. It's your average divergence over all of your training samples. But then if I take the derivative of the loss with respect to any w, because of the linearity of the derivative, d loss over any dw is going to be the average of the derivatives of the divergences for the individual training instances with respect to that parameter. Which means we need to be able to figure out this term. How to compute the derivative of the divergence for any individual uh, training instance with respect to every one of the parameters of the network. Because that's the rule we're going to be using for gradient descent, right? You're basically checking, does increasing this parameter increase the loss? If so, then I'm going to decrease the parameter. Does increasing the parameter decrease the loss? If so, I'm going to increase the parameter. That's very simple, trivial logic, right? There's no magic to it. And if I asked you, without going through the math, how you are going to modify parameters, that's the logic you would have come up with on your own. So this is just doing exactly what your brains tell you must do. So first, before we continue, we're going to talk about some basic rules of calculus, right? How did we define a derivative again, Abdullah? No, for any scalar, how did we define the derivative? What was the derivative?
It's the slope, I think.
Yeah, but how did we define it, Ibrahim? How did we define the derivative?
Derivative was a small change in your function that comes from the small change in.
The change is not the derivative, right? What was the derivative, Shangde? Guys, we just went through this, right? Equator, what is it? It's the multiplicative factor by which you multiply a small change, the small change in the input to give you the corresponding change in the output. So dy over dx is the multiplicative factor that you multiply dx by in order to compute dy, right? It's up there on for a sufficiently small increment that must hold. Now, so here is a simple pictorial representation we're going to keep using for the next few classes. If I have a function y equals f of x, then x influences y. That making sense? X directly affects y. I'm not telling you how it affects y. I'm just telling you x affects y. And then, therefore, an increment delta x is going to result in increment delta y. Right? And this is where we actually begin putting some math to it. This is a graphical representation. This edge is going to carry the weight dy over dx. I'm calling this an influence diagram, but you get the idea, right? What this means. Everyone with me? And so when I draw this, it means that delta y equals dy over dx times delta x. In general, if I write, x some alpha y using this notation, then what is the relationship between delta y and delta x? Alpha times, right? So this is the notation I'm going to be using. But that edge carries the weight that is the derivative, okay? And so I'm going to say delta x equals, delta y equals dy over dx delta x, and dy over dx is going to be on the edge, okay? And this picture is amazing, right? So suppose I have a whole bunch of variables. Y is a function of x1 through xn. How would I draw the influence diagram here? Using the same notation. Joshua. No, but how do I draw this diagram? That's going to be x1 to xn. Each of them is going to influence y. Make sense to everybody? Right, because you have, this tells me y equals f of x1, x2, xn. So x2, right? Hazim? Okay. So now using this notation, how would I introduce derivatives into this picture? Ashley. So each edge is going to have dy over dx1. I'm writing this as a full derivative because you will see in a bit that whether it's a partial derivative or a full derivative gets confusing. So I'm just going to write it as full derivatives, right? So each of these edges is going to carry its own derivative as the weight, okay? So given this now, what is delta y? Delta y is going to be what in terms of the delta x's? It's going to be the sum, right? Each one, delta x1 times dy over dx, because everything that comes in adds, right? There's going to be dy over dx1 times delta x1 plus dy over dx2, delta x2, and so on. Or in general, summation I dy over dxi delta xi. So is this notation making sense to everybody? These pictorial representations are very cool. If you understand them, then you can pretty much work out the derivative for any function because you just draw all of these influences. We'll see that in a few classes. We'll see some special cases in a few classes, right? So here is my representation for the function. So that's going to be my derivative diagram, right? Every edge just carries its derivative. And so dy is simply going, delta y is going to be the sum over all x's of delta x times the partial derivative with respect to the edge. And so just looking at this, you can also tell me what the derivative of y with respect to x is going to be. It's going to be the vector of partial derivatives, right? The picture is also telling you that story. Everyone with me? Doreen, making sense? Right. So now I have a nested function of this kind. So Heiji, how do I use the same logic here? So I think you got it right, but can you repeat that? And louder? You got it right.
How much that G?
Right, okay, so here's what we had, right? I have y equals f of g of x, right? So x influences g. That's the first innermost thing, right? And g influences y. And every edge carries what? The derivative of the output with respect to the input, right? So I can say this edge carries dg over dx, and this edge carries dy over dg. Okay, so if you look at the logic now, I know that delta y equals dy over dg times delta g, right? That's what this portion of the figure tells me. And then delta g equals dg over dx delta x. That's what this portion of the figure tells me. combine the two, and I'm going to get delta y equals dy over dg times dg over dx delta x. So what is the derivative of y with respect to x from this? What is the multiplicative term that multiplies delta x to give me delta y? This product, right? So when I chain things up, their product, their derivatives, basically the edge weights are going to multiply. This is a standard graph structure, right? I've just converted the functional representation into a graph. You begin to see how it makes sense, right? And so over here, I'm going to get what happened. Dg over dx goes over the first edge, dy over dg goes over the second edge, and so starting from outwards, out to in, you always write this starting from the out going back in. This direction is important. We'll see this later in class. So it's going to be dy over dg times dg over dx. And this is a very familiar chain rule, right? But drawing things out in this manner immediately tells you the chain rule. You don't have to think hard. You just have to write out the arithmetic. And so now here's a more complex function. I have function y equals f of g1, g2, g3, g4, many different functions of x. All of them, all g1 through gn are all functions of x. How would I draw the influence diagram for this? Anyone? How would I draw the influence for this? Thank you, Vibha. Can you say that aloud?
I'm assuming x is a scalar.
Yeah, so we're going to start off with x, right? And then x is going to influence g1, g2, and gn, right? And all of them are going to influence y. This makes sense to all of you? Right. And what does each edge carry? The derivative of the output with respect to the input. So actually over here, I think I'm calling these z's. I'm going to call, the g's are functions. I'll call the variables z's just for convenience sake. And so this is going to be z1, z2. This is my function, right? Zn. And so this is going to be dz1 over dx, dz2 over dx, dzn over dx. And this will be dy over dz1, dy over dz2, right? dy over dzn. I can just draw this figure like so. And now looking at this figure, can you tell me what the relationship between delta x and delta y is going to be? So, right, so I can just tell you that using this notation to the right, I know that dy delta y equals dy over dz1 times delta z1 plus dy over dz2 times delta z2 and so on, correct? But then what is dz1? It's going to be dz over dx times delta x, right? So this is going to be delta y equals dy over dz1 times dz1 over dx1 delta x1 delta x plus dy over dz2 times dz2 over dx delta x plus, can I group things up? Delta x is common, right? Is it not? And so I can say delta y equals dy over dz1, dz1 over dx plus dy over dz2, dz2 over dx, dy over dzn, dzn over dx delta x. So what is the derivative of y with respect to x? It's the term in the parentheses, right? Everybody with me? Make sense to you folks at the back? Right. So basically, that's what we've got. This would be the picture, right? And so just following the arithmetic that we just saw, we're going to find that dy equals delta y is the sum over all z's of dy over dzi times delta zi. Each delta zi in turn is simply dzi over dx times delta x. Group them together, and you get this lovely equation for for the distributed chain rule. You learn this in school. When you draw the picture, it becomes obvious. This is how it must be. Right? So these pictures are amazing tools. They actually help you understand derivatives. And so if I had a loss function rather than something else, and if this is what it's going to be. So these are the rules we're going to be using for computing d divergence over dw, but here's your first quote. Time's up, guys. Somebody on Zoom, can you answer the first question? On Zoom? Is there anybody on Zoom?
True. Yes, I answered.
True. Yes.
Okay. And what about the second question? Also on Zoom. Can someone answer it? What is true of the influence diagram? It graphically shows all paths and variables through which one variable influences the other. True or false, guys?
True.
On Zoom.
Both true.
Both true? Okay. You guys here agree with me? Okay. All right. Shut your laptops now that this class is true. This poll is done, right? Thank you. So, makes sense. Now, okay. So now let's go back and look at how we can compute the derivatives. I'm going to use this very trivial toy network. I'm always going to be using an MLP to compute the derivatives with two hidden layers of 2 neurons each. And within each neuron, there are 2 operations going on. Remember, first you compute an affine function of all of the inputs. Then you put it through an activation, right? So I'm going to separate the 2. Now, instead of having a bias, I've just pegged an extra input at 1 so that I can account for the bias using common rules, right? So this is what the network is going to look like. And now let me stick in all the variables. You can see all the variables over here, right? Again, just to make things explicit, the weights corresponding to the 0th input from the previous layer are all the bias terms. And then let me also label the other variables. These are just the parameters, right? What are the variables I need to label? The things that are being computed. So within each neuron, you first compute the affine term, then use that affine term to compute the output by applying an activation, right? And so if I've got Z2 superscript 3, this is the affine term for the second neuron in the second layer. Z2 superscript 1 is the affine term for the second neuron in the first layer. Y2 superscript 1 is the output of the activation for the second neuron of the first layer. So the notation, I hope, is clear to everybody, right? And of course, to learn the network, you're going to get a final output shown by uppercase Y. There's a desired output D, and you're going to compute the divergence between the 2. And our job is to compute the derivative of that divergence with respect to all the parameters of the network. Now, we know something about derivatives. The derivative depends on where you compute it, correct? So this means this derivative is going to depend on the current value of y. So what is the first thing we would need to do in order to compute the derivative? We would need to know what y is, right? We would first need to compute y, otherwise the derivative cannot be computed, right? And so the very first step, we're going to go from the beginning and we're going to compute the output. So Computation of the derivative requires intermediate and final output values of the network in response to the input, and this is what we will compute. So let me see this process of computing the output. Again, I've expanded the picture a little bit just for illustration's sake, but the process of computing the output from the input is also what you do when you actually run the neural network during operation, right? This is literally the process of inference. We often also refer to this as the forward pass. But forward pass and inference are the same thing, where you're inferring something about the input for using the network, right? So I'm going to illustrate the forward pass in these following slides. It's fairly straightforward, just using this picture. Let's consider what happens. Why is this not responding? I seem to be out of battery on this. Let me see. I'll fix this after class. Okay. So let's do this. Let's start by, for notation, I'm going to call the input the 0th layer, also the input layer, right? So the superscript 0 represents the input. Y0, I is simply the xi. This is just for notational convenience. So I can use the same notation throughout, right? And then, so again, the 0th weight, or the weight from the 0th input, is also the bias, also for notational convenience. Now consider what's happening at the very first neuron, the first neuron of the first layer. There are two things that happen. First, you compute an affine term, which is the weighted sum of all of the inputs. That includes the constant 1 term, right? So this is going to be this 1 times this weight plus this value times this weight plus this value times this weight plus this value times this weight. So the summation over all inputs of the weight from the input to the first neuron of the first layer times that input, the yi itself, right? So the superscript 0 just represents that it's the input layer. So this equation making sense to everybody? How we are computing the affine value? So that's what you'd be doing to compute the affine value for the very first neuron. You can use the same equation to compute the affine value for all the neurons. So the first thing you would do is to compute affine values, the z, right? Very simple. Once the z's are computed, you can apply the activations to each one of these z's, and you're going to compute the outputs of the neurons, right? And then from these, the next thing you would do is basically recurse the same equation, except now you're going to be using the weights of the second layer to compute the affine values for all of the neurons in the second layer. And then you would apply the activations to compute the outputs of the neurons in the second layer. And then what would you do next? Say it out, please.
The weights from the third layer applied to the outputs of that.
So you would compute the affine values of the third layer, right? And so that's going to be this, and then apply the activations and get the output of the third layer. You'd go on all the way to the final layer, right? So if I were to write all of this down as a pseudocode, I'm going to iterate going from the first layer to the last layer. So going through all the layers. And then within each layer, I'm going across the width of the layer, which may be different for different layers, right? So the first thing I did was to set the 0th layer to be the input. This is the initialization. Then I'm going through all the layers. Within each layer, I'm going across all the neurons. So I'm going left to right at each position. I'm going bottom to top. And for each neuron, I'm computing the affine value. And then passing the affine value through my activation function to get the output. Easy enough, right? Nothing fancy. We actually have some pseudocode over here, again, which is doing exactly the same thing. You have initialized the inputs, the input layer to the inputs, going through the layers. For each layer, you go through the neurons. For each neuron, you compute the affine value and then apply an activation to it. The output is the output of the final layer. So in this manner, you computed every intermediate value and the output y of the network, right? And we're going to need these to compute derivatives, right? And now here's how you compute derivatives. First, you need to compute the divergence between the actual output of the network and the desired output of the network. And then once you compute the divergence between y and d, this is for a single training instance. Again, I'm speaking only of a single training instance, right? You're going to, at the very first step, you will compute how much perturbing the output of the network will perturb the divergence. You have to go back from the end. That's the only way the computation can be done. And then, once you know how much perturbing y can perturb the divergence, the derivative of the divergence with respect to y, you take a step back and compute how much perturbing the affine terms at the output layer will compute will modify the divergence. And you can do this going backwards incrementally using the chain rule. And then you take a step back and you find out how much perturbing the weights of the output layer will modify the divergence. And then take a step back and figure out how much perturbing the actual neurons, the outputs of the penultimate layer, the last but one layer, will modify the divergence. And so you have to keep working your way back like this all the way to the beginning. So observe that what you're doing is working your way back. You want to see how much does perturbing y change the divergence, right? Then you can say how much does perturbing z change y? And then you can chain these two together, because if you know how much perturbing z changes y, and you know how much perturbing y changes the divergence, you just combine them using the rules we saw, and you know how much perturbing z is going to change the divergence. And so you keep walking back. Eventually, you can even compute the derivative of the divergence with respect to the input. How much does perturbing the input change the divergence? So let's actually see the math. Questions so far? Any questions? No? Okay. So first thing, we will need the derivative of the divergence with respect to the output of the network itself. Now, this is a property of the divergence function. We saw a bunch of different divergence functions, right? And we know that each divergence function that we chose actually had some way of computing the derivative of the divergence with respect to the output of the network. So we assume that we know how to compute this, right? Whatever divergence function you chose will allow you to compute the derivative of the divergence with respect to every one of the outputs, okay? Then we use the chain rule. Remember that if I have f of g of z, y equals f of g of z, then dl over, or if I have L equals f of y, where y equals g of z, right? Then dl over dz is going to be dl over dy times dy over dz. This is the standard chain rule. We just saw that. And so here I have this. I have the derivative of the divergence with respect to each of these y's, right? So if I want to compute the derivative of the divergence with respect to the z, it's going to be the derivative of the divergence with respect to this y times the derivative of the y with respect to the z. That's just a straight up chain rule. And since you're going backwards, the derivative of the divergence with respect to y is already known. And so the derivative of y with respect to z is all that remains to be computed. And this is going to depend on the value of z itself, right? It is just the derivative of the activation function for the neuron. And z was computed in the forward pass. And so we can stick that in here. And so we know how to compute the derivative of the divergence with respect to the affine values of the output layer. So everyone with me so far? Right? So now, if I want to compute the derivative of the divergence with respect to, say, this weight, how would I do this? How would I compute the derivative of the divergence with respect to this weight? How would I apply the chain rule? Somebody want to help me here? Akriti?
First one, the derivative with respect to y, that's the output for the input, and then the derivative will first to f dash.
Can somebody, Lakshay, can you give me the chain rule for this? Just give me the formula. What is the derivative chain rule? So it's going to be d of divergence over dw is going to be d of divergence over dz times dz over dw. That would be the simple chain rule, would it not? So if you look at this, if I want to compute the derivative of the divergence with respect to, say, this weight, then I'm going to multiply the derivative of the divergence with respect to this z by the derivative of this z with respect to this weight. Right? Straight up chain rule. Making sense to all of you guys? Right? And of course, since we are going backwards, the derivative of the divergence with respect to z has already been computed as we went backwards, right? And what is the derivative of z with respect to w? Jay, what's the derivative of z with respect to w?
It's just the affine combination.
How did we define, what was the formula for z?
W multiplied by y plus x.
Thank you. So what is the derivative of the divergence with respect to w?
X.
Just the z, right? So we had z equals, that was z1, right? I'm skipping the layer. Was y1, y0. I'm skipping the layer indices. This is just w0, I plus y1, w1, I, and so on, right? And so dz over d, whatever w, dzi over dwji is simply going to be yj. Make sense? Right, just that specific thing. And because the rest of them don't matter, right, for the derivative. And so this guy, dz over dy, is simply going to be the input again. So if I've got y multiplies by w to give you z, it doesn't matter what else is coming in, right? The derivative of z with respect to y is w. The derivative of z with respect to w is y. Very simple. We know this, right? And so that's all I stuck in over there. Make sense to everybody? Right? And so expanding this rule, I have the derivative of z of the divergence with respect to the weights of the output layer, right? Including the bias, of course. And so all of these terms are computed. These derivatives are computed. Okay? Everyone with me? We are going backwards. What is the next derivative you would compute?
Function.
Pardon me?
The function of the previous layer.
So function,
The output.
the output of the previous layer, right? So what is the next derivative you'd compute? You're going to be computing the derivatives of the divergence with respect to the y's, right? All of the y's. And so now let's do this. Let me write this out. So this part was easy, right? Now I have y. Let's just take, say, some y1, right? So y1. Now y1 eventually influences the divergence, correct? What is the path between y and the divergence? Any given y. So let's say I chose this y. Let's say I chose this y, right? What are the paths between it and the divergence? If I were to draw the influence diagram. The y is influencing all of the z's, right? And all of these are influencing the divergence. Make sense? Yes or no? Right? So what is the derivative of y, divergence with respect to y? So what is the derivative of this divergence with respect to y? Yeah, keep going, Priyanka. Yeah, but I want the derivative of this term with respect to this. Right? We just worked it out. Aryan.
Sum of all chain derivatives.
So it's going to be the sum over all of these paths, correct? And what will each path contribute? What will each path contribute? It's going to be d dive over dy is going to be summation over all i's d dive over d zi times dzi over dy. And what is this one? So let's say, let me call this yj, right? What is this? What is this term? This is simply going to be wji, right? Remember? Everybody with me? Right. So this is simply going to be summation over I d dive over d zi times wji is d dive over dyj. Very simple, nothing particularly complicated, right? When you write this back. And so if you actually work that out, you're just following this rule. Y is influencing all the z's. All the z's are influencing the divergence, right? So we're going to be summing over all of them. When I draw the network, it doesn't look so obvious, but when I draw it this way, it looks obvious, yes.
So we have to compute both the derivative with respect to the weight of that particular layer.
You need the derivative with respect to the weight simply because you're updating the weights.
And then to go back on the layer, we have
You
to
need to
also
compute the derivative with respect to the y, right? Otherwise, you cannot go back. Yes? And so, just using this simple logic, here's what we got. The derivative of y with respect, z with respect to any yi, the divergence with respect to any yi, is the derivative of the sum over all z's of the derivative of the divergence with respect to the zi times the derivative of zi with respect to yi. This term is already computed while going back. This term is simply the set of weights. And so now we have the derivative of the divergence with respect to all the y's, right? Very simple. There was nothing particularly complicated about this at all, was there? Questions, folks? Yeah.
So in this case, when we're taking the derivative with respect to the weight, we're getting y. But then in this case, like y should be like a value. How are we like using these values?
So y, remember, when you're going forward, the first thing we did was to put the input and compute of things all the way out to the end of the network, right? So all the z's and y's are known. In the forward pass, if you go way back here, the first thing we did before we did a backward pass was go forward, right? Remember we did this?
Right.
So we got the z's, we got the y's, we got the z's and y's all the way to the end. We know those values.
But then over like an entire training set, like how would you determine?
You would do this for every, I'm currently speaking for one instance, right? You would be doing this for every single training instance in your set, and then it would be computing these derivatives for the entire training set and averaging them. That make sense? Yeah. So here we are. We computed these, right? And we know how to compute the derivatives with respect to the y's. But now that we have the derivative with respect to the y's, I can take a step back and compute the derivatives with respect to all of these zi's using the chain rule, which is simply going to be the derivative of the divergence with respect to y times the derivative of y with respect to z, right? And the derivative of y with respect to z is going to be the derivative of the, what's it going to be the derivative of? The activation function, right? And so we can just plug those in. And of course, when I go back here, d dive over dy has already been computed. So all I do is multiply that by this term here, right? And then I can take a step back and compute my derivatives with respect to these weights using the same rule as before, right? The derivative with respect to any weight is d dive over dz times the corresponding y for the entire lot. And then also compute the derivatives with respect to y's using the same logic. It's going to be the sum over all the z's it connects to of the derivative of the divergence with respect to the z times the corresponding weight, right? So it's a very simple piece of arithmetic, nothing particularly fancy, and you can just keep working your way back all the way to the input. right? So if I were to compute the derivatives going back, this is what it looks like, right? I'm going to, at the very first time, I'm just simply going to be computing the derivatives with respect to the divergence with respect to the output of the network. This is dependent on the divergence function. And then once I've got the derivative of the divergence with respect to the y's, I can compute the derivatives with respect to the z's simply by multiplying that with the derivative of the activation function itself. And then I can go back. The derivative with respect to y is the weighted sum of the derivatives with respect to j, to z, right? And then the derivative with respect to z is going to be the derivative with respect to y times the derivative of the activation function. And then somewhere along the side, at the bottom, you also get the derivative with respect to the weights, which is the derivative with respect to the z times the input y, right? So again, everywhere we've been following this rule that if I've got y modifying w, modifying z, and which influences the divergence, right? The rule we are using is that d div over dy equals d div over dz times w, right? So this is this guy. And if I want the derivative with respect to y, I multiply by w, d div over dw equals d div over dz times y. So of course, you'd have to sum over all paths, but this is the basic rule that we're repeatedly applying, right? So the interesting thing is when I write the pseudocode out, here's the pseudocode that I've written. This is, for the output layer, I get the derivative of the divergence with respect to the outputs of the network. And then I can get the derivative of the divergence with respect to the affine terms and the weights. This is for the output layer. I'm just treating it specially for a reason, which we will get to in a minute, okay? And then subsequently at each layer, here's what is happening. You're first computing a weighted sum of the derivatives of the divergence at the output of the connections. And then you're complying up to compute the derivative with respect to the affine value. You're just multiplying this by a function, which is the derivative function of the activation. Now, the reason I'm writing this out is that this thing looks just like the forward pass. So what was it we were doing in the forward pass? What were the two steps in the forward pass at each layer? You were computing an affine function, a weighted sum, and then putting it through an activation. What are we doing here? We are computing a weighted sum and then putting it through a function. Right? That's all we are doing. Do you see how this looks almost exactly like the forward pass? Right? It's the same code, just going backwards. And the indices are flipped, right? It's making sense to all of you. Can you see what's happening here, right? So in terms of this, computing derivatives is essentially just about as expensive as computing the performing inference, right? So if you don't believe me, I'm going to rewrite it in this way. So anytime I put a dot on top of a variable, y with a dot on the top is the derivative of the divergence with respect to y. Z with a dot on top is the derivative of the divergence with respect to z. And look at what's happening. Y dot is an affine function of the z dots, a linear function of the z dots, right? And then z dot is simply y dot, instead of having y dot times a derivative, which is just another function, right? And so you can see how this looks almost identical to the forward pass. The forward pass, you had an affine term computed, then you put it through an activation. You do the same thing in the backward pass. You compute an affine term, a linear combination actually in this case, and then you put it through a different function, which is the product of a variable and the derivative of the activation. The only extra computation is the line at the bottom. This is the most expensive part. where you're actually computing the derivative because you've got to do this for all connections. Derivative with respect to the parameters. So everybody with me so far? Any questions? Because if there aren't any, there's a pull. Okay, so we'll give them 90 seconds. Yeah. By the way, this whole process of propagating derivatives backwards is what we call back propagation, right? I didn't explicitly introduce the terminology till just now, but it's called back propagation. Out of time. Okay, guys, time's up. So, okay, folks in class, what is back propagation? Is it the process of training the network? Okay. Is it used to update model parameters during training? No. Yes or no? Can everybody say this aloud? No. That's not loud enough, please. No. Still too faint, man. Okay, let's try this one last time. Is it the process of updating model parameters? 1, 2, 3, go. No. Thank you, right? So it's used to compute the derivative of the divergence with respect to model parameters, right? It is not about updating the model. It's not about learning. It's a simple process of computing derivatives. That's what back propagation does, right? So that's what it is. The last one is correct, right? Now, in this, I've made a few assumptions. One is that the computation of one neuron, so if I've got a Z and I compute the corresponding Y, it doesn't influence the other guys, right? I've made this assumption in my arithmetic. But do we know of any situations where that's not true? Vector activations like the softmax, right? So in that case, how would my derivative rules change? So here is what I've got. So earlier, I did zi within any layer, went into a function, computed yi, and then, so z1, z2, zi in general, went into some function, you got yi, and all of these influence the divergence, right? And so we said d dive over d zi was simply d dive over dyi times dyi over dzi, right? This was where each neuron did its own computation individually. But now we have a situation, right? And our situation is this. I have a vector activation. I have z1, z2, in general zi going in, right? And I have yn, yi, y1 coming out. And all of them are influencing my divergence, right? So how will my derivative rule for the derivative of the divergence with respect to z change? Can anybody tell me? What is this figure making sense? I know it's kind of messy, right? So given this, I'm computing divergence. What is d dive over d zi? What will this be in this case? So can somebody give me a formula for this? Katrina.
I'm thinking that we should calculate the derivative at the same time, like one vector, and then each time we have to just take this. I'm not sure about.
Okay, so somebody. Yes, yes.
You do the like dy1 and over the partial derivatives with respect.
Lovely, right? So you're going to be summing. So basically, if you look at the influence, each z is influencing every y. Is it not? Thank you. And so now what would the formula be? You just gave the answer. Can somebody else give me the same answer? I don't know.
You do, it'd be over the y times the sum of the partial derivatives of dy by
dy times the partial derivative of y over the I. And is there something missing in this formula? Summation over y, right? Fantastic. I mean, it should be summation over I. My indices are messed up. But is this making sense to everybody, right? So scalar activations, all you had was y was f of x, f of z. In the vector activation, the entire column of y's is a function of the entire column of z's. You cannot break this thing up, right? And so when I do the scalar activations, this is the scalar activation on the left. You see the influence pictures. Each z only influences the corresponding y. In the case of the vectors, each z influences every single y, right? And so in the scalar activation rule, if I want to compute the derivative of the divergence with respect to the z, it's simply the derivative of the divergence with respect to y times the derivative of the activation function, which is a very locally computed thing. But then in this case, the derivative of the divergence with respect to any z has to be computed over all the y's. So you'll be summing over all the y's, and you'll be summing the derivative of the divergence with respect to y times the derivative of y with respect to z, right? And so you can think of scalar activations as a special case where, each z has a corresponding y, right? So in the scalar activations, the derivatives of yj with respect to zi is just 0. And so let's take the special case of a softmax, right? In the case of a softmax, we're going to answer some questions. How did we define the softmax? If I have a bunch of z's, right, z1, z2, z3, zn, you exponentiated each of these guys and then you normalized, right? So does modifying one z modify the other y's? Yes or no?
Yes.
Okay, so I have a bunch of y's, okay. Now tell me this, if I increase this z, will this y go up or down? Can everybody say this aloud? Up or down? Up. Okay, and if I increase this z, will this y go up or down? Down. Okay, so what is the derivative of this y with respect to this z? Is it going to be positive or negative? Positive. Right? And what about the derivative of this y with respect to this z? Negative. Negative. So easy, right? And so I won't derive the formula, but the intuition should be very clear, right? I'm going to be summing over all the y's, d div over dy times dy over dz, right? And what is dy over dz? That's going to look like this. So this derivative is pretty much the derivative of the logistic function. It is y times 1 minus y, okay? And you can see that it's always positive because y lies between 0 and 1. 1 minus y is positive, so is y. Y times 1 minus y is positive, right? Whereas this cross derivative is going to be the product of yi and yj. Again, I won't derive this, right? But it's trivial to derive. It's absolutely trivial to derive. But it's minus of yi times yj. And since the y's are always positive, you can see, how this makes a difference, right? In that the derivative is always negative. The cross derivatives are going to be negative, and the true derivatives are going to be positive. And the intuition, again, must be very obvious to you, right? when you increase the variable, which ones go up and which ones go down. That makes sense to everyone? Right? Sometimes these formulae may not make a lot of sense, but then if you look at them just right, they begin telling their own story. Right? Every single mathematical term in life tells you a story if you know how to read it. And so this one tells you a story. I can write it in shorthand notation if I wish, but it doesn't really matter, right? So, and so that's why when I wrote my pseudocode, I actually wrote the output layer differently than the rest. Because typically in the output layer, we will use a softmax layer because it computes, what does it compute? Probabilities, right? And so there you're going to have to do the entire full computation. But again, the lower portion looks just like the forward pass, right? In fact, so does the output layer. The normalization does the, combines everything, even in the forward pass. But the codes, anyway, the point is, pseudocode apart, the concept remains that the inference and back propagation look very similar, even when you're using vector activations, right? So there are other special cases of vector activations, which we have on the slides. Please look them up. They're going to appear in the quiz, right? Now, here's another kind of activation which is not differentiable, which is different. We assume that the activation functions were differentiable. The rectified linear unit, this is called the ReLU. You're going to have encountered this in your homework. The ReLU is a rectification function. It outputs a 0 when the input is negative. It outputs the input directly when the input is positive. When the input is 0, both are there, the output is 0. So, is this function continuous? No? How do you define continuous? So the function is continuous. Okay, guys, let's understand this a little bit, right? What do we mean by saying a function is continuous at some point? If I have this function, is this continuous at say this point? Why? Because as I approach the function from here, it's going to come here, end up here. As I approach the function from here, it's also going to end up at the same point. It's continuous, right? What about the ReLU? Is it continuous? It's always continuous, right? I have this. And as I approach it from the right, at 0, it's going to be 0. As I approach left, at 0, it's still going to be 0. It's continuous at 0, right? Is it differentiable at 0? Why not? So remember, the way I defined it, the way I defined the derivative was this, rectify. So I said delta y equals the derivative times delta x, correct? So this should hold regardless of the direction of delta x. Now if I increase if delta x is in this direction, what is delta y? 0, because it doesn't change, right? So what is alpha? 0, right? Whereas if I change delta x in this direction, what is delta y? Delta x is going to be equal to delta y, right? What is alpha? 1. So depending on the direction that you're looking at, the derivative is different. So in that case, how are we going to be defining the derivative for the gradient descent rule? Right? Because what was the point we wanted? We wanted to move in a... So here's where things actually begin to get... We are beginning to invoke your intuition about what we are trying to do. Why did we need the derivative? You wanted to know which way to modify that value so that the loss would decrease. Isn't that right? So in general, you wanted to know how we... So we also said there are many directions in which you can change the value, typically, where the loss would decrease, right? So we're going to use that property over here. So in this case, really, we're going to use something called subgradients. So the ReLU over here, you can, or basically any kind of discontinuous function of this kind, where you have joints, right? There are many different lines you can draw at the joint. all of which are going to stay below the function and don't cross it, right? And so you could choose any one of those slopes as a reasonable guess for what the actual slope is at that point. And every one of those slopes is a valid value for the derivative. So to give you a better intuition, there's a lot of arithmetic about convex functions, quasi-seconds, and so on. We don't need to bother ourselves with that. In fact, it's a better thing to look at it as saying that, what happens in a continuous function? The function is sort of continuously rotating to the new point, right? So over here, you can think of that junction, that one corner, as a point of instantaneous rotation. So you can think of the line as rotating like so. It was supposed to stop at 45 degrees, but PowerPoint won't stop it at 45 degrees for me. But you get the idea, right? So you can think of the line as rotating up to from 0 to 45 degrees, right? So what does it mean? What does it mean when it's changing from 0 to 45? In a very, very, very small point, actually within a distance of 0, but you can imagine this to be infinitesimally small rather than 0, right? It's going from slope 0 to slope 1, right? And so any one of those slopes is a perfectly valid, if I say I'm at 0, if I think of 0 as an infinitesimally small point, it could be any one of those points within that little region, right? So any slope between 0 and 1 is a perfectly valid value to be using at that point as your derivative. Again, the intuition is that you can think of this as a line that just swung around smoothly. It is not smooth, but for our purposes, it's perfectly acceptable to believe that it's a function that swung around smoothly from being horizontal to 45 degrees, right? And so all of those slopes from 0 to 1 are valid values of the slope. Akriti, there's a question on your face. Do you get that? Okay. Anybody with questions in their minds or faces? Yeah. Can you say that loudly, please?
Can we randomly choose a number between 0 and 1 every time we...
You can choose any value between 0 and 1, right? Which value would you choose typically? You're going to try to go for the value that changes the output the fastest, right? So typically that's going to be 1, right? Again, speed of descent is important when you're computing when you're performing gradient descent. And so, okay, so I'll stay in one spot. Sorry, guys. We're having a problem with the mic, okay? So everybody with me on this one? Okay. Here's another activation, the max activation. Max activation is something that you're going to encounter. I'm going to walk very softly so the mic doesn't pick up static. You can analyze the mic sounds using a deep learning technique of your choice, and you can find out the pace at which I walk and who I am. So now, what's a max activation? You have a bunch of inputs. So I have all of these inputs. And this is something that's often used. And so x1 through xn or y1 through in, whatever it may be. And the y is going to be the max of x1 through xn. Okay. So in this case, how do I choose the derivative, right? This is not a continuous function. This is a continuous function. It's not a differentiable function, right? So how can I choose the derivative? What is the derivative with respect to all of these variables? So let me give you an example. So let's say static is annoying. Let's say I'm computing the value at x1 equals 3, x2 equals 4, x3 equals 5, okay? And y equals max x1, x2, x3. What is y? Can somebody say this aloud? What is y? 5, right? So what is the derivative of y with respect to x1? Y. Yes, because x1, perturbing x1 a little bit does not include change y, right? So the derivative of x1 is going to be, with respect to x1 is going to be 0. Does perturbing x2 change y? So the derivative with respect to x2 is going to be 0 as well. And what is the derivative with respect to x3? 1, because y is, that's the one. Again, simply looking at what it means, what a derivative means, is going to tell you what the derivative value should be, right? And so here's your problem. All right, I think we don't need that much time. So on Zoom, can somebody tell me, is dy over dz1 equal to 1?
No.
No.
So is it z equal to 0?
Yes.
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 Dy over dz2?
0.
0.
That's 0 too. And what about dy over dz3? Somebody here, is it 1?
1.
Right? So you get the idea. It's very easy. So we figured all of these things out. And so when you're computing your backward pass for back propagation, some of these derivatives may not exist, in which case you will use a subderivative or a subgradient, right? We call this a subgradient or a subderivative. Strictly speaking, that's not true for all functions, for some of the functions we'll use, but still, serves a purpose, right? So here's our overall approach. For the forward pass, you're going to pass the instance forward through the net, store all intermediate outputs of all computations, then sweep backwards through the net iteratively and compute all derivatives with respect to weights. And the actual loss is going to be the average loss divergence over all of the training instances. And so we are actually going to be, the actual gradient is the average. The entire process that we saw only told us how to compute the derivative for a single training instance, right? And so you'd have to average this over all of your training instances to compute the actual derivative of the loss. So the derivative of a single instance doesn't tell you the story. You have to remember, you're summing the errors across the space in order to approximate that shaded area, right? Which means that the derivative must also be the average derivative across the space. Otherwise, it doesn't truly represent the derivative of the loss. And that's what we're going to use. And so if you're training, we call this training by backprop. But again, backprop, remember, backpropagation only computes derivatives. There's a two-stage process. For all of your training instances, you're going to pass it through the network going forward. Then you go backwards and compute all the derivatives. You aggregate the derivatives over the entire training set and divide by the number of training instances to get the average. And that's what you would use to update the network. So far, so good, right? Now, when we looked at all of this, the math looked, it wasn't hard. The math was really very simple. Yeah? What? Something else happened. I'm not even sure what happened. How did that happen? The slide died. Class is over, guys. Wait. How does that happen? I'm not even sure what's happening here. Give me a... What? Now you're privy to my entire... If you ever wondered what's in my computer, the entire world knows it now. Is that the PowerPoint? Yeah. My apologies. That's not supposed to happen. And you even managed to peek into what my TAs say to one another. Okay. So when we actually wrote the arithmetic out, we had lots of summations and stuff like that, right? Looked ugly. It turns out that you can write things differently. You can write things in terms of vectors and matrices, and then the operations become trivially small. But for this, you need to be able to understand how the problem is set up and how calculus actually works in the space of vectors and matrices. How many of you are comfortable with the idea of derivatives with respect to vectors and matrices? If you're raising your hands, I'm looking at you skeptically, right? Because after doing this for many years, I am not. How many of you can go ahead and just pull out a derivative with respect to a complex vector or a matrix without looking at the matrix cookbook? The answer is probably 0, right? At least I'm not in the set who can do it. But using the linear algebraic notation makes things very, very simple, both notationally and in terms of implementation, because we have fast matrix libraries which can do things much faster than any piece of loopy code can, right? You use GPUs, you want to use matrix libraries. And so we want to restate the whole thing in vector terms. This is what we would actually do in any system. So I'm going to spend 4 minutes just setting the problem up. And then today, with due apologies to everybody, would you guys be willing to come on Zoom at 8 p.m.? Right. It's killing me, but I want to finish this stuff, right? And I'll need half an hour of your time. Okay. Raise your hands if you're okay with this. Okay. And some of you are not. But then those of you who are not will still have to see the video because you know what? We're going to be using it, right? So here's how I can set the whole thing up. I'm going to be using the column vector notation. If you're writing code, you're probably using row vector notation. You're going to have to transpose everything I talk off, right? So if I write all of the affine terms in any layer as, say, if I write all of these z's in the kth layer as a vector, this guy is just a vector of all the affine terms, right? Similarly, I can write the output also as a vector. It's a vector of all affine terms, right? And then here's a weight matrix. The weight matrix, if I have n input variables or n outputs from the previous layer, and I have m neurons over here, then I'm going to have n times m weights, right? Each of the m neurons receives n weights, right? And so this is going to have as many rows as the number of z's and as many columns as the number of previous y's. And the weight is simply going to be, the index of the weight is going to be the index of the z times the index of the y, right? So you can see how this works. Let me see the arithmetic. Maybe I got that wrong. If I just bear with me, this is going to take a couple of minutes. Maybe I'll go a minute over. This is not hard. So if I have y1 through yn, and then z1 through zm, right? So then I'm going to say z1 equals, so zm equals, right? And the input is y1 through yn. And this first row is going to be the row of weights going into the first neuron, right? And you can see how this works out, right? It's W11 times Y1 plus W21 times Y2 plus W31 times Y3 and so on. The second row is going to be the set of weights going into the second neuron. So the second index of the weights represents the output. The first index of the weights represents the input. That making sense to everybody? Once I write things out like so, then I can simply write, and then again, I can put all of the biases in a vector also. And then I can just write z equals w times y, zk equals w times yk minus 1 plus bk. Yk minus 1 is the vector of outputs of the k minus 1th layer, and zk is the vector of affine terms for the kth layer, right? And so I can just say zk equals the matrix wk times by k minus 1 plus bk. And so also, the activation function can just be written as yk equals fk times fk, which is the activation of zk. And I'm always treating everything as a vector activation. And so when I write it this way, you can see how the very complicated looking arithmetic earlier simply vanishes, right? I'm going to say y0 equals x. The 0th layer is just the input. z1 is simply w1 times y0 plus b1. It's just the weight matrix times y0 plus b1, right? And then y1 is simply f of z1, right? And so z2 is w2 times y1 plus b1, b2. y2 is f of z2. And so I can just write, this is the pseudocode. It becomes so simple when you're actually doing this with vectors and matrices, as you can see, right? So I'll come back at 8 o'clock and we'll just finish this bit and see how we can do backprop using vectors and matrices, right? Thank you, everybody.